So on this example, we're going to do a comparison of two different methods for finding the relative extrema for a function. So what I have here are two questions that I've taken from the practice test. And you can see that they both use the same function, f of x equals x cubed plus 3x squared. And over here, the same thing, x cubed plus 3x squared. Both questions are asking you to find relative extrema and to write the relative extrema as an ordered pair. However, this first one is asking you to apply the first derivative test to find the extrema, and the second one is asking for the second derivative test. So this will be nice to compare the different methods. So with the first derivative test, we're going to start by finding the critical numbers. We have our function f of x equals x cubed plus 3x squared. And the critical numbers are when the derivative is equal to 0 or undefined. So we need to calculate the derivative, which is 3x squared plus 6x. And we're going to set that derivative equal to 0. And we can solve this by factoring. We'll factor out a 3x, and that will leave x plus 2. We're going to set each factor equal to 0 and divide by 3. That gives x equals 0. Subtract 2, and that gives x equals negative 2. So we've got our critical numbers. And we're going to take those critical numbers and we're going to put them on the number line in order from smallest to largest. And this divides up in the number line into different intervals. And we want to test whether these intervals have a positive derivative or a negative derivative. And that's going to tell me the increasing and decreasing for this function. So I want to pick test points in each one of those intervals. -3, -1, and 1 will be test points in those intervals. We're going to substitute them into the derivative. So we're taking the test points and substituting them into the derivative, f prime. And it might be easier to substitute it in factored form. Sometimes factored form is easier to determine the signs. We don't really care about the number, we just care about the sign of the derivative on these intervals. So we'll use our test points, -3, -1, and 1. Substitute it into the derivative in factored form, 3 times -3. -3 plus 2. So this term is, or this factor is negative, this factor is negative, so a negative times a negative is a positive. So we have positive on that interval. The next test point, 3 times -1 and -1 plus 2. This factor is negative, but this factor is positive. A negative times a positive is a negative. So in this interval, our first derivative is negative. And then for the next one, we have 3 times 1 times 1 plus 2. A positive factor times a positive factor will give a positive. So in this interval, we have the derivative being positive and the function is increasing. So now that we've built this chart, we're going to apply the first derivative test. And the first derivative test reads the chart looking for changes from increasing to decreasing or decreasing to increasing. So we can see that we have a change that occurs over this critical number. And the change is increasing to decreasing, creating a maximum at that critical number. We also have a change over this critical number, a change from decreasing to increasing, and that creates a min. And so we know that this function has two relative extrema, one min and one max. So we have -1 being an extrema, excuse me, not -1, -2, and 0 being an extrema. We need the y coordinates, and we're going to substitute those into the function to get the y coordinates. And we also know the type of relative extrema. The type for -2 is a relative max, and the type for 0 is a relative min. So to finish this out, we just need the y coordinate, and we'll get the y coordinate by substituting our critical number into the function. So we're going to substitute -2 and 0 into the original function. It's -2 cubed plus 3 times -2 squared. It's -8 plus 3 times 4. -8 plus 12 is 4. So -2, 4 is a relative max. 0 cubed plus 3 times 0 is 0. 0, 0 is a relative min. So that's the first derivative test. Let's compare this to the second derivative test. Now, with the second derivative test, some of the process is the same. You're going to start off by calculating the derivative. So we have 3x squared plus 6x. Finding the critical numbers. We've already found the critical numbers to be 0 and -2. And then you're going to test these critical numbers into the second derivative. So we need to calculate the second derivative to be 6x plus 6. So we're going to test our critical numbers into the second derivative, 0 and -2. And we have 6 times 0 plus 6, that's a positive 6. 6 times -2 plus 6, that's a -6. Now the second derivative tells us the concavity of the function. So from this information, we learned that the critical number of x equals 0 is concave up at that value. The critical number of x equals -2 is concave down. So we put these two pieces of information together. The fact that we have a critical number along with the concavity is going to reveal to us whether we have a relative min or a relative max. By the way, if your value of the second derivative here comes out to be 0, the second derivative test is inconclusive and you cannot use the test. So we can only use the second derivative test when we get a positive or negative value for the second derivative. So we're going to look at these two pieces of information, the fact that it is a critical number and the fact that it is concave up. So the fact that it is a critical number means that we have a horizontal tangent line. So a horizontal tangent line, and you can have a horizontal tangent line in one of three ways. You can have it like this, you can have it like this, or you can have it like this. So when you have this last one here, you can see that the concavity on the left and the concavity on the right are different. So it can't be this one here. So it has to be one of these other two. And then the fact that you're concave up means it has to be this one here. This represents a graph that is concave up. And so that tells you that you have a minimum. So we now know that we have a minimum at that value. For the other one, we have a critical number, that's a horizontal tangent line, and concave down. So that reveals that we must have a maximum at that value. So once again, we get that -2, 4 is a relative max, and 0, 0 is a relative min. On this question, we want to use logarithmic differentiation to differentiate the function with respect to x. We're doing the equation y equals 4x to the x plus x, excuse me, let me try saying that again. Y equals 4x to the x to the 4th power. So when you use logarithmic differentiation, the first thing you do is to take the log of both sides. So we're going to use natural log. You can use other log bases, but natural log has the easiest derivative to calculate. So it's much nicer to use natural log. So the reason why we introduce the log into the equation is because it has a lot of really nice properties where you can simplify. So we're going to be using 2 of the properties of logarithms. Let me write those properties down on the right. We're going to use the product rule for logarithms, and the product rule says that if you have log base b of m times n, if you have a product inside your logarithm, then you can write that as the sum of individual logs. So you can write that as log base b of m plus, I got an extra parenthesis there, log base b of m plus log base b of n. So it allows us to, we call expand the logarithm. The other property we're going to use is called the power rule. And the power rule for logarithms is when you have a log, and inside the log you have an expression with a power. And what the power rule allows you to do, it allows you to take that power and move it into the position of the coefficient. So we're going to write this as p times log base 6 of m. So the properties that we're using, the reason we're using them is because within our log over here we have a product and we also have the power. And that power is only on one of the factors in the log. So that power, x to the 4th, is only on the x. So I can't use the power rule first. I have to use the product rule first. So on the left, I have natural log y. And on the right, I'm going to start by using the product rule and make this natural log of 4 plus natural log of x to the x to the 4th. And now that I have the second log with the power only on the one factor, I'm going to be able to use the power rule. So I'll use the power rule to get x to the 4th times natural log x. And now we've rewritten this in a form where it's going to be a little bit easier to calculate the derivative. We want to calculate the derivative, but our equation is in implicit form. implicit form is something like x times y equals 1. Explicit form is when you have one variable written explicitly with another. So this is explicit, and this is implicit. So when we calculate the derivative, we have to calculate the derivative implicitly because our equation is written implicitly. So I'm going to calculate the derivative with respect to x on the left and calculate the derivative with respect to x on the right. And on the left, I'm going to follow the derivative rule for logarithms. So the derivative of natural log of u is u prime over u. This is the rule that I'm following. And so the derivative with respect to x of natural log y is y prime over y. And I'm writing it this way because y is unknown. So I'm not able to calculate the derivative of y, but I can write y prime as the derivative of y. On the right-hand side, you can see that the variables match. So I'm going to be able to calculate the derivative normally. So the derivative of natural log of 4 is 0 because natural log of 4 is a constant. And then on this term here, I have a product. The product is x to the 4th times natural log of x, so I need to use the product rule to calculate the derivative. So if you'll remember, the derivative using the product rule is the first times the derivative of the second times the second times the derivative of the first. So that's a plus the second times the derivative of the first. So for us, we have x to the 4th as the first factor times the derivative of natural log x plus natural log x times the derivative of x to the 4th. I'm going to copy down some of this. Y prime over y equals x to the 4th. The derivative of natural log x will be 1 over x. And the derivative of x to the 4th, we're going to use the power rule, and that's 4x cubed. So we have y prime over y equals, and I can cancel one of these x's here. So that makes that x cubed plus 4x cubed natural log x. And then the last thing I'd like to do is to solve for the derivative. So I want to multiply by y on both sides, and that will give y prime equals y times x cubed plus 4x cubed natural log x. And then if you'll remember, the original equation was y. We've got that right here. Y is 4x to the x to the 4th. And we can substitute that in. 4x x to the 4th times x cubed plus 4x cubed natural log x. Now I'm sure there are a few other ways that we can write that derivative. For instance, I can see that the x cubed is a common factor there, so I could factor that out. And we would write that as 4x cubed times x to the x to the 4th. And in the parentheses, we would still have 1 plus 4 natural log x. So one last little simplification we can do here is that we notice that we have x to the power 3 and x to the fourth power. These are expressions, exponential expressions that have the same base, and we're able to combine those two factors together with a property called the product rule for exponents. So that product rule we're using is b to the u times b to the v equals b to the u plus v. We use this property quite often when we're multiplying. If we have x squared times x cubed, that's x to the fifth. So we're going to use that property to combine these two factors together. So we have the same base, and we're going to add the exponents. That's 4 times x to the 3 plus x to the fourth times 1 plus 4 natural log x. And if you prefer, like I do, I like to write the powers in descending order. So I would write this 4 times x to the fourth plus 3 power times 1 plus 4 natural log x. And I think that's just about as far as we can simplify it. So on this question, we want to find the extrema of f of x equals 2x cubed minus 5x squared minus 4x plus 3 on the interval from -1 to 4. So I want to point out just a little bit of nuance here, that we are looking for extrema on an interval. And this is different from what we were doing on other problems where we were looking for relative extrema. So when we look for extrema, we're looking for the highest or lowest y value on this interval. When we look for relative extrema means that you have a neighborhood around that value where it is the max or the min, the lowest or the highest. So when we're looking for extrema, we're looking for the highest and lowest on that interval, not the local extrema. So just pay attention to the wording if you're looking for relative extrema versus extrema. So in this example, we're given this function f of x equals 2x cubed minus 5x squared minus 4x plus 3. And the extrema will occur either at the critical numbers or at the endpoints. So that's where we're going to look for them. So these extrema for the function will occur at critical numbers or at the endpoints of the interval. So we have the endpoints of the interval already. We need to find the critical numbers. So let's calculate the derivative. We have f of x. We want to find the derivative of f of x. And that will be 6x squared minus 10x minus 4. And the critical numbers are where the derivative is 0 or undefined. This is a polynomial function, so it's never undefined. So we can solve this by factoring. It has a greatest common factor of 2. Factor that 2 out, and we have 3x minus 5 minus 2. 3x squared. We'll factor that quadratic into 3x and x. We can do 2 and 1. And we want to do a minus here and a plus here. And we'll set each of these factors equal to 0. 3x plus 1 equals 0. X minus 2 equals 0. Subtract 1, that gives 3x equals negative 1, and x equals negative 1/3. Add 2, and we get x equals 2. So now we have our critical numbers and our endpoints, and we want to determine what will produce the largest and smallest y value. So we're going to take our critical numbers and our endpoints. Some people like to go in order in the chart, but it doesn't matter. Negative 1, negative 1/3, 2, and 4. And we're going to substitute that into our function because we're hoping to find the largest and the smallest y value. So I've got my calculator here. And I'm going to type my function into the y equals menu. That is 2x cubed minus 5x squared minus 4x plus 3. And I'm going to go to my table. Let's delete these old values. And I want to use the values that I've chosen here. Negative 1 is an endpoint. Negative 1/3 is one of my critical numbers. 2 is a critical number, and 4 is an endpoint. So let's record those y values. We have 0, whoops, lost our calculator. 0, 3.7, negative 9, and 37. Is that 35? Not 37. 35. So then we're going to look for the highest and lowest y values. We have the highest y value of 35 and the lowest y value of negative 9. That's going to give us our absolute min and our absolute max. So this is the absolute min and absolute max. So we're asked to record these as ordered pairs. The absolute max would be the ordered pair 435, and the absolute min is 2, negative 9. For this question, we want to determine whether Rolle's theorem can be applied to the function, and if it can, we want to find all values of c guaranteed by the theorem. If it cannot be applied, we'll state NA in the blank. So the function that we want to determine is f of x equals 2x cubed minus 5x squared minus 4x plus 3. And we're using the interval of negative 1 to 3. So we want to determine if Rolle's theorem can be applied with this function on this particular interval. So let's read the details of what Rolle's theorem says. Rolle's theorem says let our function be continuous on the closed interval and differentiable on the open interval. If f of a equals f of b, then there is at least one number in c, there is at least one number c in the interval ab such that the derivative is equal to 0. So we have some criteria for Rolle's theorem. The first criteria is that the function is continuous on the closed interval. And that is true for our function. Our function f is a polynomial function, and all polynomial functions are continuous. So we know the first criteria is met for the function being continuous. The next criteria is that our function is differentiable on the open interval, and also because our function is a polynomial function, we know that it is differentiable. And if you're not sure, try calculating the derivative. And if your function, if you're able to calculate that derivative, then the function is differentiable. So then the last criteria is that we need f of a to equal f of b. This one's not quite as obvious, so we need to check that one. So for us, we need to check to see if f of -1 is equal to f of 3. We have a question mark right now. So let's calculate f of -1. That's 2 times -1 cubed minus 5 times -1 squared minus 4 times -1 plus 3. That's 2 times -1 minus 5 plus 4 plus 3. It's -2 minus 1 plus 3. And that comes out to be 0. So let's see if f of 3 comes out to be 0 as well. It's 2 times 3 cubed minus 5 times 3 squared minus 4 times 3 plus 3. That's 2 times 27 minus 5 times 9 minus 12 plus 3. Okay, 2 times 27, let's see, that's 54 minus 45, -12 plus 3, that's 9, and nope, -9. And 54 minus 45 minus 9 is 0. So we can now say that yes, f of a is equal to f of b. The y values at the endpoints are equal to each other. So we have met all of the criteria for Rolle's theorem. It can be applied to this function. So now what we want to do is we want to find the value of c that is guaranteed by the theorem. So the value of c that is guaranteed is that we're guaranteed to find a value in the interval from a to b where the derivative is equal to 0. So we're going to have some value in between -1 and 3 where the derivative is equal to 0. So let's calculate the derivative. The derivative of f would be 6x squared minus 5x minus 4. And we're guaranteed to have a value where the derivative is 0. So let's set the derivative equal to 0. And let's solve this equation. I can factor out a 3. Nope. I can factor out a 2. I've got to go back because I've calculated my derivative incorrectly. So right here on this term, the derivative of -5x squared should be -10x. So I need to correct that. So this should be -10x. And then I'll be able to factor out a common factor of 2. That leaves me with 3x squared minus 5x minus 2. And then I can factor this quadratic into 3x and x. I need a 2 and a 1, a minus and a plus. I'll be able to set each of these factors equal to 0. And that gives me x equals -1/3 and x equals 2. The final thing that I need to do here is to check to see if these values are in the interval that we're talking about. So we're looking at the interval from -1 to 3, and 2 does fall in that interval, and -1/3 does fall in that interval. So these are the values of C. The theorem guarantees that there's 1 for this function. It happens to be 2 values fit the theorem. So C is 1/3 and C is 2. Thank you for checking out my videos. Have a great day.